Hey guys, and welcome back to class again. This is video number 2 in our beginning series on electricity that we just got started, kind of getting the foundations of charge and things of that nature. Get my pen ready and let's kind of get started going. So we finished up the very last thing that we discussed. We were talking about static electricity and we were talking about this concept of like the discharge. So this movement of electrons, that's where we're at right now. This movement of electrons. And that's actually what we refer to as current, this actual flow of electrons. And that's where this video picks up, is literally we're talking about, well, it's right there, electric current, the flow of electrons in a circuit. So there's different ways you can create, you can induce, but specifically right now, I want to talk about what's known as an electric cell for a moment. An electric cell is nothing but essentially a sexy science name for a battery, is all we're getting down to. And so batteries, I like to give credit to the first cell being by Alexandro. Well, actually, his name is misspelled. I think the way you should actually spell it is with an SS, but that's in Italian. But I kind of dig the dude. His name was Alessandro Giuseppe Antonio Anastasio Volta. Now, some people will try and give like this title of first electric cell to, what was the guy's name? Louis Galvani? Yeah, Louis Galvani. Nothing against him, but he stuck pieces of metal in a frog's leg and thought that the current had to do with like the frog's leg. And Volta kind of saw it a little bit different, and he saw it was the electrolyte in it that produced the flow of electricity. So I don't do frog legs, so I'm going to stick with Mr. Volta. Plus, he's got like 5 names, and I find that cool. Essentially, though, an electric cell is nothing but like 2 different metals. You can make a very basic battery by putting a piece of copper, a piece of zinc into a acid solution, like say H2SO4, a little sulfuric acid, and that will produce a flow of electrons due to a redox reaction taking place inside that solution. So that's all that's taking place inside there. So you need the electrolyte. Like I said, that's typically a battery, or it's typically an acid. And so that's why a lot of times you'll see like batteries, as they get old, they'll start to leak. And you'll notice the corrosion wherever they start to leak when they get old. Well, that's because they're leaking out the acid. Now, batteries like this little generic battery I'm drawing a little brackets around the left, this one's known as a dry cell battery because it's got like a paste inside of it, an acidic paste. Whereas like this car battery is known as a wet cell. I guess I'm old enough, I actually remember when you went to go buy a battery and you actually got a jug of acid and you poured the acid, the liquid, into the battery yourself. I guess the only buzzkill about some of these older batteries is eventually the water part of the battery, part of the acid would actually start to like evaporate, and you would get a trapping of gas at the top, and that's why you had to be very careful about sparking the tops of these batteries, because that's where you could actually ignite the gas and blow the top off of the battery, which unfortunately I have done before. So anyway, luckily my back was turned when it actually blew. So what is amperage, or this idea of current? Well, obviously the symbol is an I, and current is measured by, take a look at the unit, it's coulombs per second. So if you remember, we talked last time that an electron has a charge of 1.6 times 10 to the negative 19 coulombs. That's your fundamental unit of charge. So say, for example, if you saw a 2 amp circuit or a 2 amp current, that's actually a tremendous number of electrons flowing through the wire. So here what we want to do is this. An adventurous student holds a 15 amp supply cord for 20 seconds. I hate to say it, but this student is probably about to look like a piece of Kentucky Fried Chicken. Well, extra crispy at least. This would be a really bad idea. But anyway, again, I think we'll learn later in the next unit, 0.2 amps, especially like through the old heart is actually enough to stop the heart from beating. So 15 amps would be an incredibly bad idea. But the question is, how many electrons traveled through the student? So we know that current is equal to basically charge divided by time. And this told us we have a 15 amp current, and it's flowing for 20 seconds. So how many electrons? Now, right off the bat, when we first look at this, the math on this is easy. Well, we got 20 times 15 is 300. Now, remember what the unit for amps is. An amp is a coulomb per second. So we've timed a coulomb per second times a second. So that means 300 coulombs is our answer. But notice, that's not how many electrons. We've not found how many electrons flow through the circuit. What we've found is the total amount of charge that flowed through the circuit. I know that there's, again, 1.6 times 10 to the negative 19 coulombs of charge per one electron. So now all I'm going to do is grab my trusty calculator. 300 divided by 1.6 exponent, where's my negative 19, and that is equal to syntax error. Awesome. Let's review. What did I just type in wrong? Apparently, I hit the answer button instead of the times 10 to. So now let's try that. Look at that number. 1.9 times 10 to the 21 electrons. 1.9 times 10 to the 21 electrons flow through. That is a tremendous amount of electrons. But remember, electrons mass-wise are very small. They have a very small charge. So you can hopefully understand this difference between charge and electrons. Now, as we move on with our notes, how do we measure current? Well, I want to leave this little picture up here for a second. Even though we haven't talked about that stuff yet, I want you to see it. Usually you measure current with either an ammeter, or if it's very, very small amounts of electricity, we can use a galvanometer. Now, on the left, this is an ammeter, and it's very easy to tell them apart. One, the ammeter you'll see actually starts at a 0 and then works its way. This one only has a single scale and apparently goes from 0 to 10 amps across the scale. Now, a galvanometer, it's actually a little bit different. First, you'll notice that the 0 is dead in the middle. The 0 is dead in the middle of the scale, and this needle can deflect both left and right inside there. Now, the measurements themselves, a galvanometer, it's essentially a compass surrounded by a coil inside of it. Which an ammeter doesn't work too much different. But galvanometer is made to detect very, very small or sensitive fluctuations. If you put very much current through a galvanometer, usually in like physics lab, what I do is use it to create like a null circuit. So if I'm playing around in a circuit, I'm trying to power it and get like it to go to 0 so that I know that there's no current flowing through the wire. And so I can detect very smallly, are the electrons headed basically, you could say left in my circuit or right in my circuit if you want to. Now, usually in lab today, I don't use either of those kinds of meters. I use galvanometers for demos sometimes. But most times in the lab now, I use, this is what we call a digital multimeter. And what's cool about the multimeter, it'll measure amps, it'll measure, we're about to talk about volts in a second, it'll measure capacitance. It's got a huge variety of stuff we can actually use. So if I was selling kitchen appliances, I'd be like, this replaces all these appliances, 1 meter. So the big thing though, and it doesn't matter which kind of meter we're using, look up in this picture. You're going to hear me harp on this, especially for students that go to a lab. An ammeter has no built-in resistance. So an ammeter, essentially, you could say, can't defend itself in a circuit. So if you put an ammeter in a circuit without, and I know we haven't discussed what this means yet, but that's actually what's known as a resistor or resistance. And it kind of limits the amount of charge, it limits the amount of current that can flow through the circuit. Without a source of resistance in the circuit, you will literally set your meter on fire or just burn the fuse. But either way, it's still a pain for me if I'm the one that's having to take care of the meters in the lab. So keep this in mind whenever we're using an ammeter. I'm going to say this big, in a series, in a series. Mr. Cole, I don't know what that means yet. Yeah, that's cool. You don't have to. It just means that anytime you're using, let's say, for example, this ammeter here. Let's say I'm drawing the wire, and I can now officially say I have totally messed this up. So let me erase a little. But essentially what I'm saying is this. Whenever I'm using an ammeter in the lab, connected directly to it, there needs to be some form of a resistor connected. You could have a wire connecting it. That's not what I mean, but it has to literally be in a series so that the electricity flowing through this meter also has to try and get through that resistor to protect it. And so that's actually the biggest problem I have in lab are students blowing fuses on the meters because they forget this discussion, which is why I'm harping on it so much right now. Now, we're going to move through a few things really quick. One, what a conductor is. You should already have a good idea of what conductors are. Like this is a roll of copper you see here. This is gold. Reminds me of a bad joke. Gold walks into a bar. Bartender goes, "Hey, you!" Get it? Go on. Hey, you? Sorry. Anyway, never promise good jokes. So a conductor is something that readily allows the flow of heat or of electricity. So you remember electricity is essentially all that's happening is electrons are being passed from one atom to the next atom. And so that's this flow of electrons. It's like a fire brigade. And some of you watching this would have no idea what that means, but it's like passing a bucket down a line of people. And so the electrons are literally passing from one atom to the next. And so you can imagine this effect. On down the line, here goes the electrons. So conductors they don't have a very hard grip on their electrons, the atoms themselves, and that's what allows these electrons to so readily jump from one atom to another and go flowing. Now, an insulator, on the other hand, an insulator is made out of a material. We can essentially say, like, if here's the nucleus, we know the nucleus is positive. Here's the electrons. Basically, it has a bit of a hold on its electrons, so it's gripping its electron, and it's not allowing that electron to leave the atom. If the electrons can't leave, then there's no flow, so there's no current, so there's no flow of electricity. We know things like rubber, plastic, glass, porcelain. You'll see these hanging overhead on high power lines. Those are porcelain insulators. You can use glass. The coating on the outside of wire is a type of rubber insulator. It's actually more, I guess, like a vinyl insulator might be a better way to say it. Anyway, sometimes there's fires started because like rats or things for some reason love to chew on these insulation on wires, and when they do, it allows the wires to make contact, and that's where fires start. So that's an insulator, something that protects you from the flow of electricity. Let's see, finishing up. So usually when we start thinking about insulators and conductors, how we measure them is what we know as resistance. It's how much something can oppose the flow of electricity. I guess people think that, like, when you lay a wire, this is supposed to be like a little 9-volt battery I sketched here. But I think people think that literally when you lay a battery, like a piece of wire, which this would be a dead short and it would get your battery hot. Hopefully you would drain the battery before you actually got it hot. But anyway, most people think that the electrons literally jump and just whee right to the other side of the battery. Most materials, it's not quite that easy for them to flow. So if you look at all the particles that this wire is made out of, you can see that it's kind of like ding, ding. There used to be a little thing on Price is Right. They'd do Plinko, I think was the name of it, where they'd drop the things down these boards and they'd bounce. This is more like what's taking place inside of the wire. And now you can imagine that with a high enough resistance, even you can build up heat because of this. It's kind of like electric friction. Now, some materials allow these electrons to go really easily from one atom to the next. And so they have a very low resistance. Even your human skin has got kind of a low resistance. Usually at some point I'll take a meter and jam the prongs into my skin and get a reading off of it. Hey, I may do it in this video, if not the next video. Should I video that? Me actually? No, not impaling myself with prongs. Now check out this unit for resistance. This Greek letter is actually a capital omega. If you're curious, lowercase omega looks like RW. But the unit is the ohm, and that ohm is how we measure resistance. Now, what's interesting, sometimes high resistance is handy. These old school incandescent light bulbs, which are kind of disappearing because I think they've been literally banned in production in America. And there's a reason behind it. They actually made more heat than they do light, so from a energy standpoint, these are a terrible design. They're a direct descendant of Thomas Edison's original carbon filament light bulbs. The problem with the original light bulbs is they produce like a bit of a smoke inside, and eventually the inside of the bulb would turn black, so it's not so much that the bulb would burn out as it would become too suited up on the inside in order for you to see the light anymore. It grew dimmer from soot. There, soot. Doggone my Alabama-ness. Anyway, we see this piece of wire inside here. Now, this is cool. Teaching school, I always had students break a light bulb, although they're getting harder to come up with, and put it under a dissection microscope or a good magnifier. If you really look close, you'll notice something about that coil inside there. It's actually, look close at the picture, it's actually a coil made of a smaller coiled wire. So this is actually a very long piece of wire coiled up inside the bulb. And what happens is the resistance of this material is so high that as the electrons travel through it, it gets so hot it glows. And so that heat, that hotness is what gives off the light we see. But like I said, when you actually look at your bang for the buck, you're giving off more heat than you actually are light by comparison. And that's why, although I was online today, I noticed you can still order these bulbs from China if you're interested. So anybody looking for some black market light bulbs, I can show you a good place to grab a few. So moving through, I'm trying to look at the time on this video to tell if we should stop, and it's 17 minutes, so I'm going to cut us off here before we continue any further with like AC and DC electricity. So we'll talk to you later. Catch you in the very next video, part 3. Bye.